Okay, the VSEPR model is a nice model that lets us take the Lewis structure of a substance and use that to come up with its actual shape. Here, later we're going to talk about hybridization and how we can sort of come up with a theory for why these shapes are taking place. But right now in this video, I'm just going to do the Lewis structures for these compounds, and then I'm going to show how I can use this handy chart that's provided by VSEPR to predict the shape that these molecules will take. Okay, VSEPR, VSEPR, even though it's pronounced VSEPR, I don't know why, is the valence shell electron pair repulsion. And it's basically based on the idea that since electrons are repulsive, all the sites for electrons are going to try and stay as far away from each other as possible. So let's look at H2CO. So C is our central molecule or atom here. We have an oxygen and we have two hydrogens. So I'll put them all in with one bond. And then I'll count electrons. I have 2 from my hydrogen, plus 4 from my carbon, plus 6 from my oxygen for a total of 12. And then I'm going to octet all of my atoms, and I'm going to make sure, don't forget to octet the central atom as well. And then I'm going to count electrons and reduce to make sure that I have the right number of electrons in my Lewis structure. So here I have 2, 4, 6, 8, 10, 12, 14. So I have 2 more than I think I should need. So what I'm going to do is I'm going to take these electron pairs off of those 2 and form a double bond instead. That should reduce my overall number of electrons. 2, 4, 6, 8, 10, 12 to the right number. And now I have my Lewis structure correct. Now, let's look at what VSEPR suggests for this shape. So, how many bonding electron pairs do I have? I have one site, 2 sites, and 3 sites. So I have 3 bonding electron pair locations. I ignore the double bonds when I'm considering this chart. And then I have 0 lone pairs on my central atom. And so I can see that I'm dealing with this section in the chart, the trigonal planar, which means that this atom is going to take on this shape. And we can see that if we compare this shape to our atom, we can see that one of these would be the oxygen and the other 2 would be hydrogen. And so we say that this shape has a trigonal planar shape, which means that it's forming a triangle and it's all existent in one plane. Note here that my bond angle is predicted at 120 degrees. Okay, let's look at CO2. Carbon, oxygen, oxygen. And again, I will octet everybody with one bond to the central. And now I'll count my electrons. 4 from the carbon, plus 2 sets of 6 from the oxygens for a total of 16. Now counting 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I can see that I have too many, so I'll make some double bonds here. There's my Lewis structure. And now, when I look at bonding electron pairs, again, remember I'm going to ignore my double bonds for the sake of using this chart. I'm going to see that I have 1, 2 possible bonding sites. I have no alone electron pairs, and so this is going to be a linear shape, where we can imagine the carbon in the middle and the oxygens on either side. The ideal bond angle here is 180 degrees. So that's how we can use this chart to go ahead and look at the number of, it says bonding electron pairs here, but I would say sites of electrons. In bonds, single bonds. And that way you'll know that you're not going to count your double bonded electron pairs as one of those electron pairs. So let's look at CO3 2-. There I've put the carbon in the center and put oxygens all the way around the outside and octeted everybody. My total number of electrons, oh, I didn't octet my central atom, there we go. My total number of electrons is 4 plus 3 times 6 from the oxygens plus 2 more. So that's 18, 20, 24 electrons to work with. So now if I go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, got extra electrons. So I'll form a double bond. The choice of where I put this double bond is arbitrary. I just happen to choose that one. And now I can see I have 1, 2, 3 sites for electrons, no lone electron pairs. So I'm dealing with this chart again, and this is another trigonal planar with bond angles of 120 degrees. I think I better do a quick example here that I wasn't planning on because I don't have any of these ones that have lone electron pairs. So let's go ahead and let's look at ammonia. Okay. For ammonia, I would have nitrogen, lone electron pair, hydrogen, hydrogen, hydrogen. I always draw it this way, but now we can use the VSEPR chart to figure out what exactly we have here. So we have 3 bonding sites, 1, 2, 3, and 1 pair of lone electrons. So 3 bonding sites and 1 pair of lone electrons are 4 possible locations for my electrons, and this is going to be a trigonal pyramidal, which means that it kind of looks like a little pyramid here where the nitrogen, why does it have a top on it? Get rid of that top. The nitrogen is sitting, and then you've got these 4, oh, that green is supposed to represent the lone electron pairs. Okay. Anyways, this would be like your nitrogen, and these would be your hydrogens, and that green would be the location of your lone electron pairs. I don't know why they put it on this one, but then they didn't put it on the bent model. So anyways, so that's how you get that. So this is a trigonal pyramidal, which is kind of like a triangle-based pyramid, and then the bond angles in here. If you did it from a tetrahedron, you'd think it was going to be 109, but the angle given by VSEPR is a little bit more accurate than that. VSEPR recognizes that the lone electron pairs repel a little more than the lone electron pairs repel a little more than bonded pairs. And so within that, with that in mind, we recognize that these all get pushed down a little bit more, and this angle between them actually ends up being a little smaller than we thought it was going to be. So instead of being 109.5, which would have been for a perfect tetrahedral shape, they get pushed a little closer together at 107 degrees. So this is the VSEPR chart. That's how we can use it to predict the shape of different molecules, and then with that we'll be talking about how these molecules might form dipoles.